All right, we're going to get started. So, I said this before unofficially, officially on the record. Welcome to week 2 of the course. So, today we're going to continue our discussion and adventure into microprogramming, and we'll get as far into pipelining as we can. But before we do that, some course administrivia. So, Lab 1 and Homework 1 will be launched this Wednesday. They'll be both due 2 Wednesdays from now, February 7th. The rest of the deadlines for Homework 2, 3, etc., Lab 2, 3, etc., are like 99% baked. Be on the lookout for them going live on the website sometime later today or tomorrow. But the first lab and the first homework will both be due on the same day. Apologies for that, but after that, we'll have staggered labs and homeworks where only one is due per week, and having them both due at the same time for the first lab and homework is a way of kind of getting that pipeline going. To what I said last Thursday, the waitlist has been cleared. I think people should probably be aware of this. So we were able to take everybody on the waitlist. There are, I believe, several, and by several I mean less than 5 concurrent enrollment students who are still on the waitlist due to a race condition. We will also be able to take them. But the waitlist, which was once longer than the original class size allotted for 152, has been cleared, and now we have on order 220 people in the class. So with great power comes great trade-offs. Over the next week or two, we're going to be testing the waters and gauging how we need to reapportion resources to deal with the increased load. So we've been talking with the administration and we've gotten some new course staff. Fortunately, we were able to find one new TA to help out with the increased load. We were also able to secure several more discussion rooms. For the first 2 weeks of class, we won't be using the additional discussion rooms. So if you look on the class calendar, you'll see everybody in the staff's office hours, times, locations, discussion hours, times, locations. Those will be the discussions for the first 2 weeks. We're going to be getting a sense based on who shows up for what discussions over the next week or so, what we need to do in terms of utilizing the extra space. So if you don't mind behaving this week like you intend to behave for the rest of the semester, we'll have trained this predictor by the end of the week so that any speculation that we do in moving our new TA and our existing TAs to the additional discussion sections will not be for naught. So we've cleared everyone. Bear with us while we kind of rejigger things and figure out exactly how we're going to manage the increased class size, but we plan to figure it out in the next week or so. All right, with that, the class notes have been finalized. I do not believe that they have been updated on CalNet Central, so please just ignore CalNet Central. These are the finalized notes. The TLDR is that time conflicts will be allowed for both the lecture and the final. The main reason being that now that we have 220 people in the course, having or not allowing time conflicts breaks the laws of physics in terms of fitting the 220 people into this 139 student room. So time conflicts will be allowed for the lecture. The lectures will be recorded. We're recording right now. We've been recording since the beginning of the semester. Feel free to come to lecture. I believe you'll get more out of it, but if you cannot, that is fine too. The lectures will be available, the ed discussion, the discussion section, so on. Lots of resources will be available. There is a final for 152, as I said on the first day of class. It is May 9th. This time has not changed, 8 to 11 a.m. There will be, in concordance with there being time conflicts allowed for the lecture, there will be an alternate final offered May 9th, 11 to 2 p.m. That is the 3-hour slot immediately after the final. We chose that slot because of it minimizing the risk of any academic integrity issues. You need to be able to make one of these. you obviously don't need to be able to make both of them. And if you take the final twice, you will not be given extra credit. If you cannot make either of them, unfortunately, that's where we have to draw the line, and you won't be able, or you at least should drop the class, because we can't accommodate extra final times beyond these 2 slots, except for properly documented DSP situations. As I said in the first class, no final for CS252. There's going to be a project instead that's presented in RRR week. Still stay tuned for scheduling related to that. The calendar has been almost completely populated. So see it for the lecture times, office hours times, and locations, discussion time and locations for both me and the course staff. As I said in the first lecture, go to whatever discussion you like, or should I say more precisely, go to whatever discussion you plan to go to longer term, so that we can get a more accurate, as I said before, accounting of how many extra discussion sections we need to bootstrap. And finally, students will be added to Gradescope by the end of the week. All right. So I believe that the administrative side of the course is converging. Any questions administratively? Yeah. Okay. Email either Raghav or Coleman, who are 2 of the TAs in the class, and you will be granted access very quickly. We've gotten a number of those emails. Emailing me only is a recipe for disaster, because I go through my email once a week, and that's just purely for my own sanity. But if you CC a TA, they will get back immediately. Any other questions? Yeah. Say that again, speak up a little bit. Around Wednesday, when the homeworks and the P-sets are posted. Any last questions? And we have several polls to send out, so stay tuned. Okie dokie. All right, let's get the show on the road. Is my keyboard working? Great, awesome. Okay, so last time we got through a whirlwind historical tour of computer architecture and processor design, both from the side of theory and practice, invoking names like Turing and von Neumann. And now we're going to get into more or less the last 50 years of innovation in processor design. And to kind of kick things off, recall from last time, what we're going to be doing is we're going to, just to dip our toes in the water, have a little bit of a digression on how to think about processor design through the lens of microprogramming. So microprogramming is a relevant topic today, but it's just a good way to view processor pipelines a little bit differently, in a way that you may have not looked at them before. So to kind of remotivate the problem, and what we're going to be doing for a lot of the first part of this lecture is going through an exercise of how to microprogram a simple RISC-V implementation. Recall that the motivation here is that, as it turns out, if you view a processor from a 30,000-foot view, kind of at the level of what some people call the von Neumann architecture, you have control, you have data path and memory, and as it turns out, one of the hardest things to get right in an implementation is control. This is exacerbated as the complexity of the instructions in your ISA increases. So in early machines, we had what eventually became known to as CISC ISAs, complex instruction set architectures, where the idea was that every ISA level instruction performed a relatively complicated operation. Orchestrating what the hardware needs to do in order to execute these complicated operations, if the way that you're doing it is through hardwired control logic, turns out to be quite complex. And a rat hole that one typically falls into is, as the ISA gets larger. As the instructions get more complicated, the hardware for both control and data path complexifies. So for example, if you have a matrix multiply instruction, you might be incentivized to build a large array of multiplication units inside of your pipeline that are only used for that matrix multiply instruction and for no other instructions. So hardware complexity scales, or at least initially scaled as a function of ISA complexity in the early days. Microprogramming was a way to push back on that idea. It was a way to say, okay, we live in a world of CISC ISAs. CISC is nice because we don't have good compiler support. They didn't know what a compiler was back then. Programs were expressed in terms of the ISA level operations, but they knew that they would be bound to implementing those instructions, so we don't have a serious compiler problem. So what we're going to do is we're going to, with very simple hardware, orchestrate the operations needed to execute these larger instructions. And the way to kind of think about them, or to think about that, was to take the ISA instructions and thinking about them as as being broken up into smaller instructions, where each ISA level instruction you can think of as a program. A program that is implemented in smaller instructions called micro instructions, and these micro instructions would orchestrate control over what is hopefully a much simpler data path. And so the payoff here is going to be a way of designing a designing an ISA that is arbitrarily complex and features an arbitrary number of instructions with an arbitrarily simple pipeline. So for, oops, you okay? Everything good? So for any ISA that you give me, within reason, I can give you a microarchitecture with a small area footprint where the only thing that potentially grows as a size of the ISA is a microcode ROM, which you can think of as the program size for these ISA instructions. Okay, and where we ended last time was to show kind of a high-level sketch for what these microcoded pipelines or microcoded processors look like. And recall, it looks similar to what you learned about in CS61C. You have a memory, you have a data path, and what looks different is in the upper third of the picture. It actually looks similar to pipelines that you learned about in 61C when viewed from a 30,000-foot view, because in 61C, you knew that you had control, you knew that you had a fetch stage, something to kind of orchestrate control, and that's kind of what the top looks like on the slide. But what makes this different is that instead of having a PC register visible, we now have this mu PC or micro PC register visible. You can think about this as the PC into the program or microcode sequence that is going to be used to implement each of the ISA instructions on your machine. So you can think of the decoder as your new instruction memory using this analogy, aka microcode ROM. This is what is going to store the implementation in micro-ops of each ISA level instruction. Traditionally, these microcode ROMs, hence the name ROM, are read-only, but naturally, when trade-offs changed, as we'll see towards the end of the lecture, they became writable because SRAMs became more profitable relative to ROMs, and so people tried to create writable microcode memories. We'll see that a little bit later, but for now, just imagine them as read-only memories. And out of the microcode ROM comes all of the control signals that you need to orchestrate the processor. And yes, this looks very similar to what you saw before. Now, if you look closely, you might be asking, okay, this is great. We have a micro PC. I know I can sequence through a microcode ROM. I can get micro-op control signals out. I can orchestrate the pipeline with these micro-op control signals. What seems to be missing that is important in this picture? Any takers? Yeah. The control logic is badly portrayed in this slide, but it is here. You can think of it as the control lines that are coming out of the microcode ROM. Yeah. The pipelining is also very badly portrayed on this slide because there's nothing inside the box that says data path, but that is where it might be. So we're going to give it credit and say that it's there. Yeah. Yeah, the regular PC is missing. So it's all well and good to be able to implement an individual micro or an individual ISA instruction. You kind of load the micro op PC somehow, and then you step through the microcode ROM, and the control signals come out, and your pipeline does different things per micro instruction. But then what happens when you hit the end? So what's not shown on this slide, again, badly portrayed in the slide, is that the PC is going to be, as we talked about last time, going back to the stored program concept where instructions live in data memory and are not discernible from program data. Instructions come out of main memory, as we had before, and the PC is interpreted by the data path as just another piece of data that is read out of memory. So the kind of intuition, the way to think about it, like right now, is that an individual instruction, even if going back to 61C, we think of instruction and data memory being different, where the instruction comes out of instruction memory, it gets decoded, data flows through the rest of the pipeline, you might interact with data memory. In a micro-coded processor, the processor itself, I don't want to use the word pipeline because pipeline suggests an implementation, but the processor data path itself is so simple that the process of reading instruction memory, or in this case, main memory, at an address corresponding to the PC is itself a micro instruction. So the process of reading instruction memory you can think of as a micro load word operation, where the instruction comes through the data path and several control signals. These are the control signals that give you the hint as to where the PC is influencing the microcode engine. Opcode and control. These signals coming out of the data path from this, call it a micro load word instruction, are going to be what inform the micro PC register to kick off the process of stepping through an ISA level instruction and switching to another ISA level instruction when the current ISA level instruction is complete. So this picture does a poor job of explaining this, but I just wanted to say that now to kind of give you some intuition for how, call it the outer loop of this architecture works, walking through ISA instructions. And we're going to see in more detail how this works in a few slides when we go through the example. Okay. This way of thinking about processor data paths, where we want a simple data path that doesn't need to change and can be programmed using these micro operations to implement more complex ISA level instructions, made a ton of sense in the 50s, 60s, 70s, 75 years ago. The logic at the time was vacuum tubes, main memory was magnetic cores, we had read-only memory. And what was interesting about the trade-offs back then was that logic, as it turned out, was very expensive relative to both ROMs and RAMs, read-only memories and random access memories that are readable and writable. So we didn't have the luxury of building sophisticated data paths because the logic was too expensive. On the other hand, miraculously, memory was cheap. And going back to, as your ISA complexity grows to infinity, the real cost of a micro-programmed data path is the size of your read-only memory, because presumably the programs, the micro-programs that you write to encode the ISA instructions is going to grow. The cost is going to predominantly be in that ROM. So if the ROM is cheap, you're sitting at a good spot in the trade-off space. ROM is faster than RAM, hence why these instruction memories or these micro-op memories were initially read-only. But we'll see that that changes soon in the future. Okay, so for this exercise, we're going to micro-program a RISC-V pipeline. This should be, you'll have to twist your head a little bit if you've taken CS61C. So we're going to be using RISC-V for this. We already have kind of the contours of why RISC-V is good. RISC came out of Berkeley. This is the 5th generation ISA. It's realistic, it's complete, it's open, small, it's extensible. We'll be using it for both education and research in the course. It's relatively clean. It was designed for, or with an I for cleanliness. So hopefully relatively easy to understand, / you probably are already familiar with it. And to get all of the specifics on RISC-V, you can either look up the official RISC-V Foundation documentation or documentation in 61C. Just as a very brief reprimer on RISC. So here is the architectural state, or at least the register architectural state for the RISC-V 32-bit ISA. So we have a program counter. Again, this I hope is reviewed. A program counter. We have 32-bit wide general purpose registers labeled X0 through X31. X0 only contains 0, which is a convention that is carried over from RISC generation to RISC generation. We also have floating point registers. We won't really use them for the rest of the class, except to make an example and further motivate microprogramming, but just know that they are there. And there is a separate floating point pipeline that we will concern ourselves with soon in the course. And coming along with the floating point registers is a status register, which encodes if anything wrong happened during a floating point operation, like if the result went to nan or infinity or something like this. The RISC-V encoding depends on the width of the ISA that you're interested in. There are several variants. Yeah. Speak up. Sorry. That's a good question. Does it say something about that on the slide? I don't know. I doubt it. The reason being that actually floating point 0 can have some weird effects, or floating point in general can have some weird effects because of dynamic range. But I don't know off the top of my head. My guess would be no, but I could be wrong. So RISC-V encodings, there's several different ISA widths. So there is a 16-bit ISA, which is for a compressed subset if you are eminently concerned about your program memory footprint. There's a 32-bit ISA, which is primarily the one that we will be working with in the class. There are larger instruction encodings that are not ratified, and we will not concern ourselves with them. Just know that they are out there. RISC-V can be extended to support additional width, additional instruction encoding widths. Here is just the top right corner of the green card in RISC-V. I believe everybody has seen this in one form or another from CS61C. So you have several types of instructions, which are each responsible for different tasks. The R-type instructions are responsible for register to register primarily arithmetic operations. So we see RS2, RS1, this is register source 1, register source 2. RD, register destination. Opcode, is it an add, is it a multiply, is it a sub, is it a bitwise, and so on and so forth. And some additional funct bits to encode additional instruction semantics. Likewise, we have an I-type. This is also a register normally arithmetic operation, but where one of the operands is now an immediate, which is encoded directly in the instruction. So that's relevant. You do not need to synthesize or construct the immediate. It's just baked into the instruction for you. And then several other types, memory types, branch types. And there's been a special, we won't really need or be focusing deeply on exactly the alignment of the different fields in the ISA, but it'll come up sporadically through the course what motivated different design choices in RISC-V. A very simple one that I want to point out right now is that if you squint your eyes and you look at the different instruction types, you'll see that specific fields like RD tend to be in the same place across different instruction types. Anybody have a sense as to why that would be? Yeah. Exactly, exactly. It turns out that you can factor your control logic and your data path so that regardless of what instruction type you're about to execute, if the same field always appears at the same offset, you're always peeling off the same wires. There's a bunch of nuggets like this baked into the RISC-V ISA that we'll hit on as the course goes on. I just wanted to mention the simple one now. Okay, so that brings us to the microprogramming exercise. So we now have a very high level view, or at least hopefully recollect something about the RISC-V ISA. And now what we're going to do is we're going to just do an exercise where we see how one would implement this ISA on a microprogrammed data path, a very simple data path, a low hardware area data path where every RISC-V operation is broken up into simpler ops. Okay, so this is the object of interest for the next 20 minutes or so in lecture. And I just want to kind of step through this pipeline and point out where it's similar and where it might be different from pipelines that you've seen already, say in 61C. So at a bird's eye view, you look at this and you might think, okay, this actually looks pretty similar to what we saw before. All the pieces are there. We have, going from left to right, we have the instruction register, we have decode logic, which is not really shown in the diagram, but when these wires out of the right-hand side of the instruction register, all of the instruction register, or all the registers are oriented so that input is on the left and output is on the right. Out of the instruction register, we see several wires coming off, some going to familiar opcode, register source, register destination fields, and some coming for immediate. Then we have the register file, which takes as input an address or an index that can be one of several things based on the mux above the register file. And inside the register file, we have the registers and the PC. And then we have an arithmetic unit, the ALU, and two registers which latch the inputs to the ALU, A and B, we'll call them. Then we have a register into a single memory. So in 61C, you may or may not have had a unified instruction data memory. For our micro-programmed simple data path, we will have a single memory, just for simplicity, both in hardware area costs and also for kind of pedagogy, that holds both instructions and data. And we have a register right before it that will latch the address into the memory. And for the moment, we'll relax this in a second, but for the moment, let's assume that the memories, both the register file and the main memory, are asynchronous read. So at the rising edge, when a value is loaded into the address register, in the same cycle, data at that address will come out of the memory. And likewise, at the rising edge, we'll assume synchronous write. So at the rising edge, any write enabled to a memory, the data at the data in port will be written to the memory. Okay, so here is our pipeline. There is a major difference between this pipe, or I keep on using the word pipeline, I apologize, old habits die hard, data path. There is one major difference between this data path and the probably pipelined data path that you saw in 61C. And that is that instead of the different sub-operations or stages being connected to each other directly by wires, there's a common data bus that all of the different pieces are connected to. And the data bus is just wires, where the important characteristic is that only one person or entity or unit can own the data bus at a given time. So with that in mind, the way to view this is the only way to send information from stage to stage is over the data bus. The data bus can only be used by one stage at a time. So instead of doing an operation in a single cycle or doing an operation in a pipelined fashion where we have multiple either ISA instructions or micro ops executing concurrently, the way that we're going to execute an ISA instruction on this architecture is sequentially, temporally over multiple cycles, sharing this data bus. Okay, so with that in mind, let's have some fun with it. Okay, so here, this is going to be a little awkward. I think what I'm going to do is I'm going to turn this around so that I can actually see what I'm drawing. Is it going to work? Okay, beautiful. Okay, clear all drawings. All right, so let's, for argument's sake, say that I want to execute a RISC-V add instruction, register to register. So I look up two locations in the register file. I do an add at the values in the register file at those locations, and then I write the result back at another location RD also in the register file. Can anybody tell me the first thing that I'm going to have to do? Assume that we're looking at this pipeline and reset has been called, so all the logic is wiped, but I have my micro PC set to the first thing that I need to do to implement this ISA level add. Does anybody know what I need to do first? Yeah. Yeah, how am I going to do that? What do I have to do? There's one, I'll add one thing because it's especially unclear on the slide. This input to the address into the register file is a constant which corresponds to the PC register in the register file. Okay, with that, continue. Anyone? What do I have to do? You were right. Yeah. Very good. Let me see if I can. I'm going to get a little less thick of a line here. Yep. Okay, so the first thing we're going to do, we have our microcode ROM. Our microcode ROM control signals are coming out. The control signals that we need in order to grab the current instruction, again, the control signals are coming out, so our micro PC is correctly pointing to the first thing that we need to do in this add operation. The control signals are going to, first of all, drive reg select. Say that we need to get the PC out of the register file. Drive reg select so that this special index into the PC goes into the register file. This is going to drive the output of the register file to this triangle symbol, which is a tri-state. A tri-state is just a switch like a transistor. So you can programmatically either connect the input to the output or disconnect the input to the output, kind of like a diode, actually. So the second thing we have to do is drive this tri-state. That's going to dump the current PC on the data bus. Everybody gets it because the data bus is shared everywhere. Where do we have to write it? We have to write it to the memory address register. This is going to be our lookup into instruction memory. In order to write enable that register, we also have to drive this signal MALD write enable, call it. Okay, anything else this quote unquote micro operation? I think we're good. Okay, what's next? Someone volunteer. What happens now that I have looked up instruction memory and recall asynchronous read? So at the moment of the next step, the rising edge of the next cycle, we're getting the contents of instruction memory at that PC out of the main memory. What's next? Not quite yet. And the reason why not quite yet is because I don't even know that I'm executing an add yet. I'm executing a micro-op which corresponds to fetch. All I've done so far is read out of instruction memory a blob of data, which is going to be an ISA level instruction. Yeah. Yes. What do I have to do now that the instruction is sitting basically here? What do I have to do to decode the instruction? Where does it need to go? Close enough. So what we're going to do is we're going to, and I'll just clear. I think it's easier to clear. So what we have to do is we have to drive the tri-state out of instruction memory. Right here, we have the PC sitting still in this memory address register because I have not done anything with the write enable since I first set it. We're going to be driving our common bus. The common bus is going to go to the input of the instruction reg, and To lock in the instruction, we're going to drive the right enable for the instruction reg. Okay, clock tick. Next thing. Sure, go for it. Mm-hmm. Say that one more time, a little bit slower. Mm-hmm. Yeah. Mm. So it's not, the address isn't in. Tell me if this answers your question. The address is not in main memory. At the end of the first cycle, so at the beginning of the first cycle, we're selecting what control signals to drive to get the PC so that we can look up main memory. By the end of the first cycle, we're about to write enable the PC to the memory address register. In the next cycle, we have the PC, it's just locked in the address register of the main memory, and the current instruction is just flowing out of main memory. And it's just sitting there. Something to note here is that in this next stage where we grabbed our instruction and we shoved it into the instruction register, we did not do anything to mem adder. It's just sitting there to give us a stable signal throughout the pipe. Next step, what do we have to do? Rising edge of the clock, next cycle. Now we have the instruction flowing out of the instruction register, the decode logic, which is not shown. What do we do with it now? Remember, this is register to register add. Yeah. Very good. Does it matter RS1, RS2, A, B? You could do it either order. Add is commutative. You could either take RS1 and shove it into A, or take RS2 and shove it into A, or any permutation thereof. Probably good to stick with a consistent convention. So we'll say that RS1 always comes first, RS2 always comes second, RS1 goes into A, RS2 goes into B. So just to show that graphically, we have the instruction reg, the instructions coming out. We're going to decode. Oops, sorry about that. RS1 is going to flow through the register file. I get the contents of the register file out. I'm going to activate the tri-state and dump that first operand on the bus. That's going to go up to the A register. I'm going to write enable the A register to lock in that operand, and that is the next step. Okay, rising edge of the clock, what's next? Spoiler alert, it's similar. RS2 to B. I haven't given us any flexibility in what we want to do next. I'm not going to draw this again. We're going to go instead of RS1 to RS2. We're going to, and we get that by changing the reg select signal. We're going to drive the bus in the same ways we did before. We're going to drive the signal up to A and B, but this time we're going to write enable B. We are not going to write enable A because we want to store the value that we had on A beforehand. Okay, rising edge of the clock. Now we're in business. Now we have the two operands, both in those two registers, A and B. And what's next? ALU up. Okay, finally, after all of this, we can do the actual thing that we want to do. So what we're going to do, I'm going to clear this one more time. So we have A and B flowing out. They're going into the ALU. We need to select our ALU op. So the control signals coming out of the microcode ROM need to tell us that this is an add as opposed to a sub or whatever else. We're going to do our ALU operation. It's going to come out. We're going to drive the tri-state. We're going to get our data on the bus. It's going to go up to a register file. We're going to write enable the register file with the reg W signal, and we're going to take the reg select signal and indicate that we're about to do a write to register index RD. Again, off of the same instruction that has been pegged in the instruction register for the past 3 or 4 cycles. So we only write enabled the instruction register once, and it's been helping us orchestrate the show along with reg select and the other signals since then. Okay. Are we done? Sure. Yeah, sure. So if you think about on my left hand the different ISA level instructions where my finger is the PC, and think on my right hand as the micro PC, which walks through the micro instructions needed to implement each ISA level instruction. So what I meant by reset was whenever you move from one ISA level instruction to the next, you're going to need to reset your micro PC to go back to a common prefix of operations, which now that we've gone through this exercise, I can define as the fetch sequence. So it's going to need to bounce around more than the ISA level PC, and that bouncing around is what I meant by reset. Yeah. Yeah, we still have to increment the PC. So remember here, a RISC-V add instruction on paper takes the sources, does the add, writes it to the destination register, but we also have to increment the PC. There's more that goes on in the background. And on this microprogrammed data path, we need to explicitly increment the PC. So I'm not going to show it, but what you need to do to increment the PC is do all that you did to actually do the add operation, but just to increment the PC, read it out of the register file, lock it into either operand register A or B, lock an immediate, which is in the case of RISC-V's 32-bit ISA for add 4, because it's a byte addressable ISA, into the other register, perform the add, and then write back the result of that to the register file at the PC index. So it's a whole sequence of 3 or 4 more micro programmed operations just to write the PC there. Okay. This seems rather slow. It takes many cycles to implement an add. That's ultimately fine for our exercise, because the whole point of this is to take very simple hardware and implement more complex operations, with, again, the payoff being that we will not have to change our pipeline as our operations get more sophisticated. But I do have a question for you all. So we said that the main memory and the register file were asynchronous read, just for simplicity. We get the data out immediately. What if I told you that the main memory took typically many cycles to complete, which is realistic given machines today? You put an address in, it takes several cycles for the data to come out, and on the slide, this is signified by the busy signal. So there's an extra control signal coming out which says the data is not ready yet at this memory. If it is the case that our main memory takes multiple cycles, let's say it takes 5 cycles. I think that that's going to be enough headroom to make the point. Is there, in the spirit of, what's your name? You asked about the PC, or who asked about the, or who mentioned the extra operation that we need to increment the PC? I didn't just make up that someone told me that the PC needed to be incremented by 4. Some friend in the middle of the class tipped us off that we had to increment the PC. In the spirit of that being something that we need to do, if our main memory takes, let's say, for argument's sake, 5 cycles to return data to us, does anybody have an idea for how to performance optimize this microprogrammed add? Any ideas? Yeah. Yes. Awesome. So what we did originally was we sent the PC to the address of the data memory. We're now incurring that 5 cycles of dead time where, based on our original strategy, we're not doing anything. And then we get the instruction, we plug it into the instruction register, we read the operands out, we do the add, we write it back. And then, kind of implied, we update the PC at the very end. We can't do the actual arithmetic operation on source RS1 and RS2 before we get the instruction into the instruction register, but we can increment the PC. So the better way to implement this operation, if you're trying to reduce the number of cycles that it takes to implement, is to first get the PC over to the main memory. While you're waiting for the main memory to return, sneak in the PC and an immediate to the ALU so that you can get the next PC value, write that back to the register file, and then hopefully that finishes, because everything is owned by the same common data bus, right before the read from main memory returns actually gives you your instruction and then allows you to execute the rest. Does anybody see a problem with that? Yeah, we don't even know if we're executing an add before the add instruction encoding comes back from main memory. But what I just said was we're going to sneak a PC plus 4 into the shadow of knowing what instruction we have to execute. If there's other instructions like branches or jumps or things like this where the PC is changing in different ways, we're going to have to adjust how much we increment the PC or offset it by in order to make the jump or the branch land at the right location. And so if you look at the actual microcode for implementing branch or jump, the optimized code is going to increment the PC in the shadow of reading from main memory so that in the common case, we save those cycles. But if what we end up having to do is eventually jump or branch, we're going to have to correct ourselves. So we're going to have to add a step to correct the PC and massage the offset so that it ends up landing in the right place. Okie dokie. All right, so now let me go back. Yeah.
Branch like offset that for
That's kind of the flavor of what you have to do. I can't remember off the top of my head exactly what the PC relative offsets are, but that's kind of like the common repair style operation that you have to do. Yeah. The micro instructions, it depends. That's a good question. And that actually is a good segue into the rest of the lecture. So I'm going to say stay tuned. Stay tuned. Any other questions? Yeah.
if we just have like a for aliens, so
Yes, you could. You could. There's several ways to implement this. Actually, this slide is vague as to which way it should be implemented. But three ways of implementing it are roughly, A, you have a special adder that sits next to your register file, which is solely responsible for incrementing the PC. I think that that's what you had in mind. And the real reason for doing that is that you don't need to waste cycles on the common data bus, any cycles, either for getting stuff to the ALU or writing stuff back to the ALU. So that's arguably a good design because the common data bus is sacred. Another implementation is what I was implicitly walking through a few minutes ago, which is you've got to synthesize the four, you've got to read the PC out, you've got to get both of them to the one ALU that you actually have, you've got to do the ALU op, you've got to write it back to the data bus, and you've got to write it back to the register file. Yet a third implementation might be creating a special ALU op where instead of doing like add plus the two inputs, you do add plus like the A input, and then you just create a +4 constant, which is derived from the special ALU op. And that implementation is kind of somewhere in between. You don't need a special adder, an additional adder, and you don't need to occupy the data bus twice to get the operands to the ALU, but you still need to occupy the data bus once to get the PC operand to the ALU. So these different implementation choices, there is no laws of physics which says that one is always right. What is right is constantly changing as a function of the different costs in the design. As the cost of an add, like the circuit to do a 32-bit add, goes to infinity, one would prefer two of those three implementations that require only one add circuit, namely the ALU, as opposed to a special ALU in the decode stage. But again, this is traded off relative to the common data bus, whether the common data bus's time is really truly precious for this PC plus 4 operation is a function of the latency out of the main memory. So there's all sorts of things going on here, and it's all about how to balance them for your current trade-offs to get a sense for what the best design point is? Good question. Other questions? Okay, so let's continue on. Let me get out of annotation mode. That is it for our interactive super session for the day. And now my keyboard is no longer working. Let's get the mouse back. Okay, micro instructions as register transfers. This is just some gratuitous text to give a small window into what we just did. Different operations, MA, so MA is the memory address. The acronyms are, I tried my best to make sure that they're all on the slide, but if any acronym is confusing, just ask on Ed. Okay, so popping up a level, what's interesting about this is while we have a very different way of temporally orchestrating an instruction relative to what you may have learned in CS61C, the steps that are taken are quite similar, as they should be, because the semantics of the ISA instruction have not changed. We still need to fetch from memory, we still need to grab stuff from the register file, we still need to do the ALU op, so on and so forth. So we still need fetch, we need decode. One can think of there being an extra step for register fetch, but it is semantically, we were doing this before, just implemented as direct point-to-point connections. We have our ALU operations. We have potentially memory operations, depending on whether we're doing a memory instruction. Something interesting about this pipeline relative to, or I keep on, again, saying pipeline, relative to this data path, relative to the CS61C pipelined architecture that you may have seen when taking that class, is that microprogramming is and gives you a lot of opportunity to optimize for specific instruction types. So in the CS61C style microarchitecture, you are sending signals to at least the address input of the data memory on every instruction. Whether you actually take the result of the data memory depends on whether you're doing a memory operation, but you are entering into a memory stage. There's not a memory stage bypass in the traditional CS61C pipeline. With a microprogrammed pipeline, you of course do not need, if you are not doing a memory operation, to talk to the memory at all, except to grab the instruction out at the very beginning. Nor should you, because that occupies the data bus for a cycle. Okay, these are, just for background reference, microcode sketches corresponding to instructions like what we went over a few slides ago. So instruction fetch, we separate it from what the actual operation is doing because it's the same for every operation. For every ISA level instruction that you need to execute, we need to get that instruction in the instruction register. And that allows us to kick off the next sequence of micro operations. And then we have ALU, which is kind of like very similar to like what we saw in the example. And then it gets a little bit interesting. So like I said, you can optimize for memory operations. You'll see a different sequence for doing things like load word. And then JAL and branch get especially interesting. So what I want to say about these for now is that depending on whether, let's take branch as an example, depending on whether you take the branch or do not take the branch, you'll have to either change your PC to the branch target or not. So branch, we typically say that branches are conditional, jumps unconditional. So branch, we're going to be evaluating a predicate, and depending on the evaluation of that predicate, jumping to this new destination or not. So we need a little bit more in terms of semantics for our microcode engine to understand when we either execute a few more micro ops, which are going to correspond to massaging the new PC and setting the PC register to it, or jumping back to the fetch routine and changing the ISA level instruction, or getting ready for the next ISA level instruction immediately that we are to evaluate. So the really kind of like key new thing is this line here. We check to see if the predicate is true or false, and if it is true, then we're going to, or if it is false rather, we're immediately going to go to instruction fetch, otherwise we're going to fall through. And for that we need a slightly new semantic, which was already on the slide, but I just want to kind of call it out here so that the picture from the beginning of the lecture is complete. That is this condition signal. So the condition signal, which we kind of glossed over originally, is going to tell us, okay, in the middle of an operation, some extraneous event happened. We need to, using my terminology from before, reset the micro PC to a common routine, flip to the next ISA level instruction, and continue from there. And this conditional or con signal is going to come up a few more times in the lecture, so I just wanted to kind of call it out. Okie dokie. All right, so that gives you a sense for, with this relatively simple data path, how to implement more complex operations. Now, one thing that we did not go over, we kind of stepped through assuming that there was a magic source for these control signals like reg select and the various data bus enable signals. We assumed that we just kind of got them out of thin air based on what we knew that we needed. We did not talk about how the microcode ROM is actually implemented. What are its inputs? What are its outputs? How are these different control signals actually encoded? So that's going to be what the rest of the lecture is about. Okay, so if I were to stick you on a desert after walking through the previous example and asked you to sketch for me at a high level, not a very optimized microcode ROM, but a microcode ROM which would be capable of mechanizing the steps that we just walked through in the register to register add example, you might come up with something like this, where you have a ROM. The ROM is going to take several inputs to determine the address. That's going to give you your control signals that we were drawing on the slide a few minutes ago. And what comes out is both those control signals and some information that tells us what micro PC we're going to need to execute next. The micro PC is going to feed back and become a part of the address to help decide what the next place in the microcode ROM that we need to read from is. So what are the pieces here? So we have the micro PC, we have the instruction opcode, we have a condition which corresponds to that. Is the branch going to be taken, and do I need to reset the micro PC to the beginning of the fetch sequence, or do I just keep on going? And then I have the busy signal, which is this: if I have a memory which is taking a variable number of cycles, I need to make sure to pause things while I'm waiting for the memory to come back. So these are kind of the four extraneous signals that we pulled out of our pipeline from the earlier example. And we're going to use that to determine what the next thing that we read out of the microcode ROM is. This all should make sense intuitively. If we're currently busy, that should give us a clue that we should pause our orchestration through the microcode ROM. If we have a condition bit which is telling us to branch, this is going to tell us that we're going to have to recondition the address into the microcode ROM. These are the various reasons that our into the microcode ROM PC might not change at the usual cadence of increase by one address or whatever the width of the memory is per cycle. So one note, micro PC and opcode, we split these out. This is a little bit of an optimization, but I'm just kind of showing it like this for now. The reason that we split these out is because regardless of, for many instructions, what the opcode is, the micro PC of events that you have to perform does not change. So for example, in the previous slides, if the example we did was sub, like take RS1 from the register file, RS2 from the register file, write it back to the destination register. If it was sub, all of the same control signals like reg select, the write enable to the instruction register, etc., they would have all had to have been set in the same way that add would have been set. The only thing that would have changed was the opcode of the instruction. So from an optimization perspective, this is a way of kind of decoupling those two signals. And sometimes the opcode tells us that the micro ops that we need to execute are completely different. So sometimes you can view it as an optimization, and sometimes you view it as a way of reading from a completely different part of your microcode ROM. Okay, so just taking this at face value, this is pretty high level, but let's just kind of get a flavor for how much this costs based on this schema for reading and or looking up and getting data out of the microcode ROM. How many address bits is this? Well, it just comes from the width of these different inputs. So the microcode address is just the width of the micro PC, the width of the opcode, and then +1 for each of these status bits. So no magic here. How many data bits? This, again, is just a function of the width of the micro PC, because I said that it's going to split out to the micro PC and the control signals, where the control signals are however many is needed to orchestrate the data path. In the case of our example from the previous slide, if you count all of them, it comes out to 18. So 18 control signals. And so what that gives us is a total ROM size of the usual 2 to the however many address bits you have, and that is times by the data width. And so if you actually look at the contents of the ROM, we'll get back to that memory size in a few slides and how to optimize it. But for now, if you just look at the contents of this ROM, the contents look something like this. Oops. So for every location in the ROM, you have a different operation that we orchestrated from the previous slides in the example. So we have fetch 0, fetch 1, fetch 1. Notice that fetch 1 is repeated twice. That's just a way of encoding how, if the main memory takes a variable number of cycles, we're to wait and not continually increment from fetch 1 until we move on. It's just an implementation detail that arises from variable latency memory. And then we proceed with the rest of the fetches, and then we have different blocks of instructions that correspond to the different instruction types that we are to perform. And this is kind of meant for illustration purposes, because if you don't optimize your microcode ROM, this is kind of the contents that you get. And a lot of it is undefined. So you notice that there's a lot of X's in the micro ROM address, where if you have an X for an address, this is not something that really makes sense. You have to fully specify your address. So this is just to say that if you kind of naively lay out your microcode like this, a lot of your address bits are going to be no ops, or going to be ultimately not useful in determining where you should be in executing inside the microcode ROM. So this is just kind of like for illustration purposes. If you were to think about the schema that we had for building the address from the previous slide, this is the contents of the microcode ROM that you end up getting. And like I said before, yeah. Yep. There we go. It would, yeah. For RISC-V, it probably would. I guess it's unspecified for our example, but that would make sense. Yeah. Because like Func3 and Func7, I think it's like used to specify extra information about certain instructions like shifts. And that conceptually is just more opcode information that's been split out for implementation and other reasons. Yeah. Other questions? Okay. So this is kind of the layout of memory that you get. And like I was kind of alluding to, so this is kind of the size that you get at the end of the day. So now we kind of have like an abstract size number of locations and the width of each location. You kind of have a sense for the contents on the previous slide. And this is more precisely how you compute the size. So on the one hand, we have a common sequence of steps. We have a few locations in this microcode ROM which are responsible for fetching. But after that, we have these instruction groups. These are like sequences of operations that are used to, or you can think of them again as taking that analogy, the micro program for each ISA level instruction. So you have groups of instructions. Each instruction has a number of steps. The steps can vary between instruction, but most of them take around 5 operations. So the example that we gave a few slides ago where we were walking through the add, that was twiddle 5 instructions. And so This gives you a sense for how many total steps we need to be able to encode in our microcode ROM. So like the 3 for fetch plus the number of steps per group times the number of groups. This gives you, if you take the ceiling power of 2, 2 to the 6 bits for the micro PC. The opcode is 5 bits. This is going to be for encoding the operation and for designating the control signals. And so this gives you a total size of, if you just do the arithmetic, 25 kilobytes, which without a baseline may seem large, may seem small, but we can do better. And this is the way to think about optimizing your microprogramming. So we already walked through several examples for how to optimize microprogramming: overlapping operations, reusing the same fetch routine for every instruction group, taking advantage of the fact that some instruction sequences touch data memory and others do not, and not actually writing down the operations for touching data memory for the ones that do not. Those conspire, those types of optimizations, some of them at least, conspire towards enabling us to shrink our microcode ROM capacity. And that shrinkage comes from compressing the microcode ROM in one of the 2 dimensions that every memory has: the number of entries in the memory, the depth or the address space, and then second, the width. How many bits are encoded at each location in the ROM? So if you're a microcode ninja, you think along these lines to get more and more functionality into your microcode ROM. So you can shrink the height or the depth. You can do this by combining different operations in your microcode so that the number of steps that you need total to store shrinks. Taking the fetch sequence out and reusing the same fetch sequence for every instruction is a great example for how to reduce the number of microcode entries you need to support. And then the second, the microcode ROM width. This gets back to a question that was asked earlier, which is how to, in a more compressed fashion, encode the 18 or however many there are control signals which you have to read out of the microcode ROM. So the question is, do I actually need to store all of those bits there for each entry, or is there a more compressed representation so that the width of the microcode ROM shrinks? Now, suffice to say, once you do a best practices pass at applying both of those techniques, this is a better design, or this is the architecture of what a better design might look like relative to the schema that we saw a few slides ago. So what this picture shows is, at a 30,000 foot view, the same thing as what we saw before. You have the microcode ROM, no magic here. It takes input address bits, data bits come out. You get something to do with the micro PC and the control signals that go to the rest of the pipeline, and then the rest looks different. So in this optimized representation, the magic happens in how we orchestrate and define the address into the microcode ROM. So what we're going to do is, instead of having like those different fields like condition, busy, where a lot of them I said were basically irrelevant for a given operation. For example, if you're doing a microcode ROM step, which is like loading a value from the register file into the A and B operand register, I don't need the busy bit. And so it really should not be an address bit. So once you factor that out, you get a design like this, where the address into the ROM is just the micro PC. This should seem a lot more intuitive than shoving a bunch of other control signals into the microcode ROM. You're sending in a micro PC. Now you can kind of think about the microcode ROM as kind of like a micro instruction memory. Again, taking our analogy of a microprogram being, or a sequence of micro operations being a microprogram. And now, based on some additional information that we get out of the data contents, so we've taken what was before used as address and we're now encoding it in the data payload of every microcode operation, we're going to decide how to update that micro PC in the next cycle so that we can get the next value out. In particular, what we see just from the picture, and we'll go over the options in a little bit more detail in the next slide. Several options for how to update the micro PC are, on the one hand, you might just update it by adding 1. So you increment 1 to the micro PC, you select that updated micro PC is the next one that you want to store, and then you use that to index the microcode ROM. This is kind of like the common case of, I know what instruction, ISA level instruction I'm going to execute. I have my micro PC pointing to the first micro op location in my microcode ROM, and I'm just going to sequence through, no magic, just as simple as can be, reading the straight line microprogram that I've written. And then there's several other options that have to do with whether we're currently waiting for memory, busy, which means conceptually that we're going to kind of pause and not update the micro PC, whether we need to take a condition, which is going to tell us that we need to go back to fetch, recall. And then depending on the opcode, we may need to update it in several other ways. But this is kind of the new microarchitecture that we're dealing with. So going back to the slide, we have this terminology coming out of the data is not the micro PC that we're going to use next, but some metadata, which is going to hint to us how we need to update the micro PC. This is called micro PC jump. And depending on what micro PC jump comes out of the current microcode entry that we read, we're going to do several things. So this is just kind of repeating what I just said, but a little bit more systematically. So if the symbol which comes out is next, we're going to increment the micro PC. This is the common case. If the symbol that comes out is spin, we're going to wait for memory. This corresponds to when busy is high. Fetch, dispatch, and then ftrue, ffalse is going to reset us back to fetch in the case that a condition evaluates to true, where condition is this out of band signal which comes from the data path based on the evaluation of a predicate in the ALU, which I evaluate on a branch instruction. And now, with this new schema for stepping through our microcode ROM, we get a quite sensible microcode ROM contents, which I believe will come across as more intuitive than the first one. So, oops, in all of its glory, we have our fetch routine. The fetch routine is going to start at fetch 0, go to fetch 2. The contents of the microcode ROM at fetch 0 is just what we went over in our example. We're going to set MA and A to PC. So the A being set to PC is the optimization that we were talking about earlier, where while we're waiting for main memory, we're going to update the PC with PC plus 4. So we're simultaneously going to update MA and A. And I just actually want, because it's not kind of like visually obvious, I want to just describe on our pipeline what that looks like. So there's a cool trick that you can use in this pipeline to improve your throughput to the various units. You can only have one writer to the bus at a time. So there can only be one driver to the data bus. But there can be as many readers as you want in a given cycle. So when you read the PC out of the register file and drive the common data bus with the PC, you can simultaneously write-enable the memory address with the PC, which is going to get your instruction out, and also lock the PC into one of the two operand registers by enabling either ALD or BLD. So that's where, going back to this slide, if you see MA comma A, it's a broadcast or a multicast, technically. You're driving the common data bus, and you have multiple people reading the common data bus. So this is exactly what we saw before. IR next is going to be equal to the contents of memory, just like what we had before. Then we're going to do the PC increment operation, and then away we go with the next block of micro operations depending on what instruction group we need to evaluate for, where a group again is kind of a group of micro-ops which are going to be symmetric about like an opcode, like add and sub would be grouped together to save space. Okay, so here's the payoff. The payoff here, as I have hinted several times, is that you can come up with an arbitrarily more complex RISC-V instruction or otherwise, and our little pipeline from 10 slides ago need not change. You have the same basic operations, they share a common data bus. You can orchestrate these more complicated operations by just adding to the microcode ROM. So for example, if you had a memory to memory add instead of a register to register add, where you're reading from the main memory multiple times, you're writing to the main memory multiple times, here's the microcode sequence for that. No need to change your pipeline. Awesome. And so that's the payoff. This pipeline will get you whatever you need. So if you only learn one pipeline from the perspective of what's the minimal amount of hardware that you need to run any interesting program, this, actually you can go simpler than this, but this is a good kind of starting point. So just a few more slides, just some terminology to give you a sense for different ways that people have thought about optimizing microcode. So back when microcode was invented, this kind of concept of implementing complex ISAs using simple pipelines, given the trade-offs at the time, this idea just took off. So it was really popular, and people came up with all sorts of interesting paradigms for optimizing their microprogrammed data paths. So I just want to spend like 2 slides outlining what those are. So one kind of dimension that people explored was these two kind of not competing but disparate ways of looking at microcode encoding, horizontal versus vertical microcode. Horizontal microcode is microcode where the width of your ROM, your microcode ROM, is relatively large. And the reason that it's large is that you feel, given your data path, that there's more things that you can do concurrently in your data path, which will hopefully lead to fewer micro-ops per instruction. So the benefit of a horizontal microcode is you can sometimes, if you design your data path correctly, do more work per cycle. The downside of a horizontal encoding is that if you're not very careful, the contents of the microcode ROM are very sparse. Most of the bits, the control signals, in the microcode content are either no ops, which is to say like X, don't cares, or you're just otherwise having to set them to 0 because you weren't able to use that part of the data path concurrently with other parts. To kind of get around that, a different school of thought was vertical microcode, which is the opposite. So you have a very tall or deep microcode ROM and very narrow entries, where the number of control signals is far fewer. You can think of a Turing machine back from last lecture as the tallest vertical microcode machine ever, because there is one control signal, whether you want to read or write the tape. Finally, this is the last thing that I want to talk about today, and then we will break, and then tomorrow or Thursday, we'll get into pipelining, which is kind of a natural evolution, one step separated from optimizing microcode, is this neat idea called nano encoding. So this is kind of trying to get the best of both worlds of vertical and horizontal microcode. The way to think about it is as follows. If you start with a horizontal microcode scheme, you end up with this problem where a lot of your control signals are sparse, which is to say like no ops, or you might end up in a situation where, and this can be true for horizontal and vertical microcode, you have many chunks of microcode in your ROM, which are all basically doing the same thing. And that's because lots of instructions are doing very similar things. For example, add and sub and bitwise, and these operations are all orchestrating operands into the A and B registers in the same way, and the only thing that differs between them is the ALU op. We already separated the ALU op, so we're not suffering from this kind of code repetition problem in that exact example. But this problem of repeated code still leads to a bloat of microcode. And so what nanocoding proposes is you can kind of think of it as subroutines for microcode. So just like if you have a common sequence of instructions or common subprograms for implementing larger programs, you don't want to just copy those for every caller in your program because that wastes a lot of space and instruction memory. And so what the microcode people came up with was the exact same idea, just in microcode. So now what we're going to do is we're going to add a level of indirection where instead of encoding the control signals directly in the microcode ROM, we're going to encode a pointer, or what is conceptually a pointer, into a second level of microcode ROM called the nano instruction ROM. And that's where the actual control signals live. So now, if you have a common set of operations, you can just look up the second level using this nano pointer, if you will, and not only compress the representation of the control signals if there's a lot of spatial redundancy, but if there's a lot of redundancy in the address space, you can also implement what are tantamount to very simple subroutines. So it's just kind of, the point here is that when people realized that microprogramming was so extensible and flexible, they have come up with all sorts of ways to optimize around it. Okay, so we're going to stop here. It is 12:32. We'll start with pipelining on Thursday. Thank you very much.